everyone, and I welcome you back to the drone technology. And we'll start up with unit number 5. And the image, as you people are familiar with, it's a drone. And for most of this people, you might have seen in science fiction movie, a common tool for popular hobbyist. See them capturing breathtaking aerial footage of films, inspecting infrastructure in hard to reach places, and even delivering packages, as we have seen in the previous unit. They have become an undeniable part of our modern technology landscape. But the technology is far from stagnant. In fact, it evolves at a desired pace, and we see today is purely a glimpse of what to come in the future. That brings us to the focus on the discussion. As we see from the title slide, we are here to explore the future trends in drone technology and the safety innovation part. This presentation marks the fifth unit of this course, and it is designed to take us beyond the drone we know today and into the realm of what coming next. We'll be looking at the cutting edge development that are set to define what these unmanned aerial vehicle or UAVs are capable of. The quadcopter you see here is a marvel of modern engineering, but it represents just one point on a rapid acceleration curve. The future promises drones that are smaller, compacter, and more resilient and more autonomous than we might have ever imagined. Over the next few minutes, we'll embark on a journey through this exciting future. We will begin by examining the core innovation in drone design, focusing on two major parallel trends: miniaturization, which is the drone, which is the drive to make drones smaller or more portable and increasingly autonomy, the quest to make them think for themselves. From here, So, as we move forward, let's dive into the core of our topic, the fundamental innovation in drone design that are paving the way for the future. The slide gives us a fascinating roadmap to the key areas where progress is most pronounced. At the highest level, the entire evolution of drone technology can be understood through two powerful parallel forces, miniaturization and increased autonomy. These aren't just buzzwords, they represent the primary direction in which all the research and development are heading. First, let's talk about miniaturization. This is the relentless push to make drones smaller, lighter, and more efficient. We are moving from the larger aircraft sized UAV that was once defined as the industry to device that can fit in the palm of your hand. This trend isn't just about making drone more portable or convenient. It's about opening up an entire new possibility. A small drone can operate indoor, navigate complex and cluttery environments, and be deployed more quickly and discreetly. It lowers the barrier to entry for business and individual, making the technology more accessible for a wider range of tasks. The second most major force in increased autonomy. This is a journey from a drone being a remote controlled puppet to become an intelligent, independent agent. Early drones requires a skilled pilot, constant attention to every moment. Today, we have features like GPS-based flight path and return to home features. The future, however, is about giving a drone high-level objective, like serving this entire farm of sign for crop stress and having it figured out the detail for itself. This involves planning its own flight path, avoiding unexpected obstacles, analyzing the data it collects in the real time, and makes decisions based on the data without human intervention. This is where artificial intelligence and machine learning comes uh, becomes absolutely critical. So, what's making this possible? The slide points to the key collaborator, advancement in sensor technology, actuator, and power storage. Think of these as the drone sensors, muscles, and stamina. Modern sensors are incredibly small yet powerful. We can now pack high resolution camera, thermal imagery, LiDAR, and a host of other sensors into a small frame, giving the drone a rich understanding of this environment. Better actuator, the motor and the control allows for more precise, stable, and energy efficient flight, which is essential for both navigating tighter space and excluding complex autonomous maneuvers. And finally, power storage. The battery has always been a drone's biggest limitation. The breakthrough in lithium polymer and other battery technology are extending flight time, allowing drone to fly farther and carry more, making them truly viable for demanding commercial application. These advancements directly fuel the expansion of drone application across numerous sectors. In the military, miniaturized drone provides critical intelligence without risking personnel. In agriculture, autonomous drone monitor vast area, applying water or pesticide with pinpoint accuracy, which improves yield and reduces waste. In logistics, companies are evolving the last mile of delivery, getting package to customer far and more efficient. And in the security, drone provides aerial surveillance for large facility or offer first responder crucial sky in the sky, crucial eye in the sky during emergency. As far you see, the key future trend are smaller size and great autonomy are not just separated by goals. They are deeply interconnected, each driving and enabling each other. The small drones need more autonomy to navigate its environment, and greater autonomy is made possible by the advances miniaturized component we have just discussed. In the next few slides, we are going to explore these two trends in much detailed manner, starting with the fascinating challenges and achievements in the world of miniaturization.
Truly understand the importance of autonomy, let's look at how it is being applied in real world right now across military, commercial, and public sector. The level of intelligence we are seeing is that system is already transforming complex operations. The military has been a driver of drone technology since a very long time, and autonomy is a key area of focus. The autonomous military drones are capable of operating both efficiently and inexpensively. The capacity of these systems are profound and raise raise significant ethical questions, as they are even being set to kill opposing soldiers. The prime example of this advancing technology is the Shield AI, the hive mind drone. This system is designed to assist both law enforcement and armed forces. It can operate in a complex environment, interacting with its surrounding to detect the environment and even recognize people, providing invaluable real-time intelligence and support, especially in an urgent situation. While military applications are powerful, the growth of autonomy in commercial and public sector is equally transformative. We have seen a rapid rise in automatic drone navigation, where drone use autopilot with built-in AI to follow checkpoints and perform automated patrols without direct human intervention. In the world of delivery and logistics, autonomy drones are being developed that are capable of carrying significant payload by up to 60 pounds and flying distance of up to 6 kilometers to deliver essential supplies and medical items. For surveillance tasks, AI-powered drone can now not only collect real-time data, but also analyze the data and make decisions independently. And in the precision agriculture, Internet of Things enabled, drone can autonomously follow preset flight path to collect data or spray pesticide with incredible accuracy. So, what does the future hold? The outlook is one of the continuous and rapid advancement. The process is artificial intelligence and deep learning with undoubted continues to enhance drone autonomy. We can expect to see drone with even more sophisticated decision making and problem solving capacity in the near future. This will lead to their increased integration into more sector, resulting in more efficient and safer operation across the border. However, this technology growth must be balanced with careful consideration of societal impact. As the system become more capable, the ethical consideration and the regulatory workframe that governs them will have to evolve right alongside of the technology. To understand how we achieve the stable flight needed for this autonomy, we need to revisit some of the core principles of physics. Before we delve deeper into multi-rotor stabilization and flight mode, it is essential to revisit two fundamental principles of physics that makes flight itself a possible thing. Both fixed wing and multi-rotor relies on this core concept to generate the lift required to overcome gravity. These are Bernoulli's principle and Newton's third law of motion. Let's first look at Bernoulli's principle, which is illustrated in the aerofoil diagram. The principle describes the relationship between the existing speed of the fluid, like air, and its pressure. It states that as the speed of the fluid increases, its pressure decreases. This is critical for understanding how a fixed wing drone generates lift. The wing of an aircraft, known as an aerofoil, is shaped with a curved upper surface and a flattened lower surface. As this wings move through the air that flows around over the curved top surface must travel a longer distance than the air flowing underneath. To cover longer distance in the same amount of time, the air on the top moves faster, and according to Bernoulli's principle, the faster moving air exerts less pressure than the slower moving below the wing. This pressure difference between the top and the bottom surface result in the net upward force, which we call it as lift. While the Bernoulli's principle is key to understanding fixed wing flight, the operation of multirotor is more directly explained by the Newton's third law of motion. This famous law states that for every action, there is an equal and opposite reaction. This is the fundamental principle behind how multirotor drone achieves lift and thrust. The drone propellers are designed to act like fan, pushing a large mass of air directly downwards. This downward push of air is the action. In response, the air exerts an equal and opposite force back on the propellers, pushing the propellers upward. This upward force is the reaction, and this is the lift that allows the drone to take off and hover. It is important to note that this principle also applies to thrust generated by fixed wing propellers, which pushes the air backward to propel the aircraft forward. In essence, you can think of an fixed wing drone using a shape of the wing to create a pressure difference that pulls it into the air, while the multi-rotor drone uses its propeller to push itself up into the air. With these principles in mind, let's now look at how these are applied in specific design of fixed wing drones. For understanding of the core physics, let's now apply these concepts directly to the design and operation of fixed wing drones. Unlike multirotor that rely on pure vertical thrust, fixed wing drones are a masterclass in aerodynamic efficiency, using their shape to manipulate airflow and achieve flight. Key to fixed wing drone flight is the shape of its wing, which is called as aerofoil. As we discussed with the Bernoulli's principle, the airfoil is designed with a curved upper surface and a flatter lower surface. This specific shape forces the air to travel faster over the top of the wing, which in turn creates low pressure under the wing compared to the higher pressure area below it. This pressure differential results in the net upward force that we call it as lift. Generating lift is one thing, by controlling aircraft is another. This is where the control surface comes into play. These are small hinged sections on wings and tail that manipulate the airflow to change the drone's altitude and direction. To control the drone's roll or its side-to-side tilting, it uses ailerons located on the wings. To control the pitch, which is the nose up or down movement, it uses elevators on the horizontal part of the tail. And to control the yaw, the side-to-side movement of the nose, it uses rudders on the vertical part of the tail. Of course, for the wing to generate lift, the drone must move forward. This is where the thrust and drags comes in. The thrust is the force that pushes the drone forward through the air and typically generated by propellers or small jet engines. Opposing this forward motion is drag, which is aerodynamic resistance the drone encounters as it moves through the air. To maintain a steady forward flight, the force of thrust must be greater enough to overcome the force of drag. This reliance on aircraft aerodynamic lift is precise, what makes the fixed wing drone so efficient, that are generally much more energy efficient than multi-rotor, especially for longer duration and long distance flight. However, this efficiency comes with a trade-off. Their flight envelope or the range of their performance capacity is typically characterized by higher speed and significantly less maneuverability when compared to multirotors. Because of this, the optimization of the wing design and overall shape of the airframe is absolutely crucial for maximizing the drone's endurance and range. On our next slide, we will look at the specific control system that manages these surfaces. We just identified the primary control surfaces on fixed wing drone, the ailerons, elevator, and rudder. Now, let's look at the control system that brings them to life. How does the command from the pilot or the autopilot translate into a physical movement of these surfaces to steer the aircraft. Let's quickly review how each control surfaces work. Ailerons are responsible for controlling the drone's roll. They work by creating a differential in lift on the wings, which causes the aircraft to back or tilt to one side. Elevator, which is located on the horizontal tail stabilizer, controls the drone's pitch or its nose up and down motion. It does this by changing the angle of attack of the horizontal stabilizer. Finally, the rudder found on the vertical tail stabilizer controls yaw. It, it detects it deflects the airflow, which pushes the nose of the drone to left or right side. These surfaces are physically moved by small motors called servos, which operates based on the command sent from the flight controllers. This all comes together in the flight control system, which functions as a continuous feedback loop. The flight controller is the brain of this operation. It constantly receives inputs from two sources: the pilot's command sent via the radio transmitter and the data from the drone own onboard sensors like the IMU and the GPS. The flight controller processes all this data and then send the output signal to the servos. These servos then move control surface to manipulate the drone's flight path as required. Modern flight controllers for fixed-wing drone can do much more than simply rely on pilot's command. They are capable of providing stability augmentation, which means that they automatically make small adjustments to keep the flight smooth. They also enables powerful autopilot function, including complex waypoint navigation, where the drone can autonomously follow a pre-programmed flight path. This method of using control surfaces is fundamentally different from how multi-rotor drone is controlled. In our next slide, we will compare this to the control system used for multi-rotor drones. We just saw how a fixed-wing drone uses physical control surface to steer. A multi-rotor drone, however, operates on a completely different control philosophy. It has no ailerons, rudders, or elevators. Instead, it achieves all its movement and stability by precise and independent controlling the rotational speed of each of its motors. Just in a fixed-wing drone, the flight controller is the central processing unit, act as the brain of the entire operation. Its primary objective is to receive and produce a constant stream of data from its various onboard sensors. The most important of these is the IMU, or the Inertial Measurement Unit, which provides the flight control with data on drone's orientation, including its pitch, roll, and yaw, as well as its acceleration. Another key sensor in is the barometer, which measures atmospheric pressure to help the drone maintain a constant altitude. And of course, the GPS provides the drone's geographical or a geographical position, which is essential for navigating and autonomous flight mode. After processing all this incoming sensor data, the flight controller sends the command out to the electronic speed controller, or the ESCs. Each ESC's job is to regulate the speed of their assigned brushless motor, and it does so independently of each other. It is by making thousands of these small adjustments every second to individual motor speed that the drone is able to achieve complex maneuvers and maintain its stability. Every movement from hovering in place to flying forward is accomplished by varying the thrust from each propeller, while the fixed-wing drone control its flight by deflecting the air with surface. The multirotor control its flight by directly manipulating thrust. This method is less energy efficient but allows for a greater maneuverability. This constant process of adjustment brings us to the important concept of aerodynamic stability, which we shall explore in the next slide. I have talked a lot about how drone is controlled, but a related and equal important concept is stability. In aerodynamics, the stability refers to an aircraft's tendency to return to its original flight path after being disturbed by an outside force, such as gust of wind. It is a crucial characteristic for both safety and ease of control. There are two main types of stability we need to consider: the static one and the dynamic. First, let's look at the static stability. This is defined by the initial tendency of the aircraft to return to its original equilibrium state immediately after being disturbed. There are three possibilities. An aircraft with a positive static stability will immediately start to return to its original state after being disturbed. This is desirable characteristic for a predictable aircraft. An aircraft with neural static stability will simply remain in its new disturbed state and will not try to correct itself. Finally, an aircraft with negative static stability, which will continue to move further away from its original state after a disturbance. This is slightly unstable and difficult to fly. Static stability describes the aircraft's inertial reaction. But what happens over time is described by dynamic stability. This is defined as the tendency of an aircraft to damp out oscillation over time after a disturbance. Again, there are three steps with positive dynamic stability, and any oscillation will decrease over time until the aircraft settles back to steady flight. This is the ideal safe condition with neutral dynamic stability. The oscillations will remain constant and never stop, and with negative dynamic stability, the oscillation will actually increase over time, getting worse and worse until this aircraft become uncontrollable. This is crucial for drone because a multi-rotor drone is inherently unstable. It has a negative static stability. It is only through the constant high-speed correction made by the electronic flight controller and the sensor, like the DJI EA2 system picture here, that it can fly. Electronics are what provides the stability. This electronic stability is the foundation for the different flight modes that pilots uses, which we'll explore in the forthcoming slide. We just established that for multi-rotor drone, stability is provided electronically by the flight controller. This ability assist the pilot is the foundation of various flight control modes that are available on most drones. These modes essentially determine how much the drone does for you, ranging from no help at all to a great deal of assistance. Let's look at the two most fundamental modes. First, we have manual mode. In true manual mode, the pilot has direct and unfiltered control over drone's movement. The flight controllers provide no electronic stabilization or assist whatsoever. The pilot's stick input are translated into motor's commands. If the pilot lets go of the control, the drone will not self-correct itself. It will continue along whatever the altitude or the trajectory it was commanded to follow. Because of this, flying in manual mode requires a significant amount of skill and practice to master. It is preferred mode of FPV drone racing and acrobatic freestyle flying because it grants the pilot complete authority over the aircraft, but it is extremely difficult for beginners. For this reason, most people begin their journey with stabilized mode. This is the first and most crucial level of electronic assistance. In this mode, the flight controller actively helps the pilot to work to maintain level flight. If the pilot lets go to the stick control, the drone will use its sensor to automatically return to the level orientation. The system also automatically corrects for external disturbance, such as gust of wind. The pilot still has full control over drone's direction, but the drone itself handles the thousands of micro adjustments needed every second to stay stable. This assistant makes the drone significantly easier for beginners to fly. So we have a clear distinction. The manual mode provides total control without a safety net, while the stabilized mode provides an auto leveling safety net that brings that makes the flight more accessible. But the assistant doesn't stop there. Modern drone often offers even more advanced flight mode, which we will explore in the next slide. We just covered the stabilized mode where the drone assists the pilot by keeping itself level. Modern flight control can take this assist even further by using additional sensors, automate more of the flying process. Let's look at two of the most common advanced flight modes: altitude hold and GPS hold. First is the altitude hold mode. In this mode, the drone will automatically maintain a constant altitude. It is achieved by using a barometer to measure atmospheric pressure or, in some classes, an ultrasonic sensor to gauge its height above the ground. With altitude hold engaged, the drone manages its vertical position, freezing the pilot control all horizontal movement. This significantly simplifies the flying because it removes the need for constant throttle movements to keep the drone from drifting up or down. This allows the pilot to concentrate more on the task like framing a photography or navigating around obstacles. The next level of assistance is the GPS hold, which is also known as position hold mode. In this mode, the drone uses its onboard GPS data to maintain both constant altitude and fixed horizontal position. If you engage this mode and let go of the control stick, the drone will stop and hover in the precise spot, actively using its motor to fight against the wind and maintain its coordinates. This capacity is ideal for applications like aerial photography and videography, as it provides a perfectly stable tripod in the sky from which to capture image and video. It is crucial to remember that for this mode to function correctly, the drone must have a strong and reliable GPS signal. These advanced modes represent another layer of autonomy, making complex tasks much easier and safer to perform. The next logical step is to have drone not just holding a single position, but to navigate between multiple positions on its own. We will look at these fully autonomous navigation mode in the next slide.